COVID-19 in recent years due to its rapid spread and proliferation. And COVID-19 has had a very serious impact on our lives and work. So we follow the general trend of machine learning and artificial intelligence. We proposed a hybrid model to detect COVID-19. Our model uses local binary patterns, LBP, to implement feature extraction in the pre-processing phase. Validation classification results are obtained using a random vector function linking RVFL network. In addition, to reduce chance due to a single division of the training and validation sets. The existing dataset is fully utilized for multiple divisions to avoid the selection of chance hyperparameters and models that do not have the ability to generalize due to special divisions. We use cross-validation to reduce the chance and improve generalization. In the paper, 10 full cross-validation is used for validation. Our hybrid model combines the advantages of both models to achieve accurate and rapid prediction of COVID-19. Finally, we experimentally demonstrate the usefulness of our proposed model for advancing the level of diagnosis. It can help healthcare professionals to accurately identify COVID-19. The next section shows you how the model works. First, I will explain the principle of the LBP algorithm. What is LBP? LBP is a widely used feature extractor, an operator for characterizing local texture features of images, with the significant advantages of rotational invariance and grayscale invariance. It was originally proposed by T. Oyala in 1994 for texture feature extraction. It is mainly used in face recognition and target detection. When LBP was first proposed, it was defined by selecting a pixel point as the central pixel point and using its value as a threshold. The neighboring pixel values around it are then compared individually with the central pixel value. If it is higher than the central pixel value, it is marked as 1. If it is lower than the central pixel value, it is marked as 0, as shown in phase 7. Let the central pixel point be 6. Then calculating it as defined gives this result. And then arranging these numbers as specified gives a binary number, which is finally converted to decimal. In this way, the pixel value is described by the LBP, which reflects the textual characteristics of the block of images, if the process is expressed in terms of a formula, as shown in this equation. However, the initial algorithm only works in areas with a fixed radius size, and the LBP algorithm still does not work if it does not match the predefined radius size. For this shortcoming, the domain of the improved LBP algorithm is extended to an arbitrary neighborhood and the shape of the domain becomes circular. The optimized LBP algorithm specifies a random number of pixel points in the neighborhood of the radius. However, as the number of samples increases, the variety of binary patterns increases dramatically and too many of them are not suitable for texture feature extraction. Therefore, it is crucial to achieve the best possible representation with a small amount of data, making full use of it. To overcome the above problems and further improve the performance of the LBP algorithm, Oyala et al. Proposed an equivalence pattern to reduce the pattern types of the LBP operator. If a cyclic binary number has at most 2 transformations from 0 to 1 or from 1 to 0, these are called equivalence pattern classes. Fig 8 below shows a schematic representation of several equivalence modes. The RVFL model is a special single hidden layer neural network. The main idea is to use the augmented nonlinear kernel raw data learned in the hidden layer to improve generalization. The RVFL and Elm models are similar in structure, where Fig 9 is the RVFL model and Fig 10 is the Elm model. The green line in the diagram represents the direct connection between the input and output layers. The weights of the blue lines do not need to be calculated. They are generated randomly. The letter H in the figure indicates the features of the hidden layer. X marks our input features. S is the input weight of the RVFL framework, and E is the input weight of the Elm framework. As RVFL is a concise planar network structure, RVFL is faster in supervised learning and training with good generalization performance. It uses fewer samples for training, and the network can achieve the required accuracy within a given region of the dataset. RVFL improves generalization performance by learning from the implicit layer of the nonlinear kernel raw data. In order to validate the performance of the model, we evaluate the model in several aspects and compare it with free state-of-the-art methods. One of them, the WABC algorithm, uses WE to extract features from city images. The advantages of the ABC algorithm are then combined with fewer parameters and simple calculations to find the most suitable solution to the problem and to validate the Covid-19. It is well known that the Fourier transform is used to transform a signal. The Fourier transform signal is decomposed into a Fourier transform for its constituent frequencies, and the altered function has different combinations of forms of sine waves. However, the Fourier transform also has some disadvantages. For example, if accurate localization in the time domain is required, all signals in the corresponding frequency domain must be analyzed. The wavelet transform is used instead of the Fourier transform because it has more variables. The ABC algorithm is an optimization method. The bees in the algorithm are classified into three types: honey-picking bees, observation bees, and scout bees. By simulating the honey-picking mechanism of row bees, these three types of bees have different jobs, but they are interchangeable under certain conditions. The second algorithm, GLCM-GA, is a hybrid structured model. In this case, GLCM performs the extraction of image features, while the GLCM-GA model uses GA for optimization. Finally, the experimental results are obtained using a feed-forward neural network classification function. The network classification function, if two pixels in an image have their orientation and the distance between them has been determined, then their spatial relationship can be calculated using the GLCM. Features of image textures. Features of image textures are represented as image grayscales. GLCM responds to spatially relevant features of an image using four features: energy, entropy, contrast, and homogeneity. The GA algorithm mimics the necessity of Darwin's evolutionary selection process and is an efficient global search method. Essentially an efficient global search method. As the algorithm is trained, it can obtain more and more valid information during the search process. More and more valid information is obtained during the search process, and this valuable information is applied to the following algorithm. The algorithm becomes increasingly effective by accumulating search information in this way. The most important feature of the third element is that it learns more efficiently than traditional learning algorithms, such as single-layer feed-forward neural networks, SLFN. More efficient than traditional learning algorithms, such as single-layer feed-forward neural networks, SLFN. The overall structure of ELM consists of an input layer, a hidden layer, and an output layer. The ELM is unidirectional bidirectional because it satisfies a one-way propagation process. Each neuron is the output of the previous neuron and the input of the next neuron. The network structure of the L model is the same as that of the SLFN, except that instead of using the traditional gradient-based algorithm, the traditional gradient-based algorithm has been tried and tested in the neural network, while using random input layers in the training phase using random input layer weights and biases during the training phase. The Elm training SLFN consists of a random feature mapping and a linear parameter solution. Finally, the experimental part is explained. In order to demonstrate the stability of the model, 10 experiments were conducted to find the sensitivity, specificity, precision, accuracy, F1, MCC, and FMI of the model, and finally to find the mean and variance, as shown in Table 2. We also experimentally compare our model with other state-of-the-art models to further validate the feasibility of our model, as shown in Table 3. Our model was the best in terms of sensitivity, specificity, precision, accuracy, MCC, F1, and FMI in detecting COVID-19. In conclusion, the model proposes a non-contact diagnostic system. It has fast and accurate characteristics. It has been experimentally proven to be used for COVID-19 diagnosis and to help doctors screen patients. The experiment investigated the ability of RVFL to predict COVID-19 outbreaks. However, limitations of the study were identified. For example, RVFL currently indicates a single sample category, using only time series data samples. In future research, attempts could be made to include more sample categories. In this way, we can recenter better data and significantly improve the model's